Hey guys, so a few months ago I recorded on a new moon day and I was wanting to share the video, but I never did. And I was making this, I was kind of writing this out on the video. Now, I ended the video when I still felt like I just had too much to concentrate on, like I was still trying to figure something out. But I want to show you guys later. Might have been that evening, but I had figured out, or the next day, I'm not sure, but I had figured out something very, very interesting that I don't think I would have caught from my own code. So I haven't shared this code on this channel, but basically it deals with lambda calculus, deals with iterating expressions and stuff. Now I want to show you guys something. So if you have these different Catalan trees, there's different ways you can form expressions that have a binary shape to them, which means each function has a left or right child, or it has you could have 1 or 0 children, but that's a different type of function, so you wouldn't even worry about that for this. This is specifically searching through all the possibilities. Now, you have a certain number of these, and I think it's 40 different ones. So if you have 5 nodes, you would have 40 different, I think 40 different types. And I was going through and I was checking them, and I realized that this configuration right here in my code, which I made years ago, like a couple years ago. This is code that I haven't shared online, but or on this channel, but this code was iterating through all these expressions so that you could, but it was using the fact that you had a binary tree to go through this. Now the funny thing is I recorded this video, which I'm about to show you, and in this video I'm using these numbers that I came across, and I was trying to search for something. I was trying to figure something out. What I didn't realize was I had a bug in my existing code already. And this helped me to figure it out because I didn't have a lot of good test cases. It was just like very minimal. The test cases for this algorithm were very like basic fundamental. It was basically just the basic initial building blocks and then nothing really too complicated after that. And for some reason, I just thought that it was working, like it was actually doing it correctly because it was iterating through all these expressions. It was actually skipping this one. It was skipping an expression basically that represents a tree that goes out on both sides and then goes out further on both sides. So on the left side, that child has a left child, and on the right side, that child has a right child. And instead of finding it, it would basically skip over because of the way that I'd coded it. It was just kind of some sloppy coding with not enough test cases, and it wasn't like I formally verified the code or anything like that. I was just trying to get some things to work in C so that I could go and formally constructed things later on, using these tools. And so I'm going to play for you guys this video, and then the video ends before I really had figured anything out. But what's funny is that later on I did figure something out. So anyway, hope you have fun, and here's the video. This is crazy. I was just taking a walk, and then I found like this really narrow path to the side, and there were 2 spider webs, and I could not get around them, so I decided to go. I wanted to see what was on the other side, so I decided to go further down this wider path and then veer off to the right to go around it, and I couldn't find it. And then I came back on the path eventually behind where that little narrow path was, and eventually I went back how I came back and then found a dead end, and I found a little sign that it was for this disc golf course, and the sign was 5 par 3 270. So I thought about that, And I was thinking, like, wait a minute. Like, because I was thinking, like, is this just, like, I'm just praying and walking, and I'm thinking, like, is there, like, a meaning to this? And I was thinking, like, well, okay, what is, like, 3 times 5? What's 3 to the power 5? Or 5 to the power 3, actually. And I was like, oh, well, let's see, 125, so the difference is 145. I'm like, no. Sounds like a function, like 3 par 5. Like, as though par was an infix function. 3 par 5 would be 270. And then I thought about the lambda calculus with the Catalan numbers and the permutations. And I was going to figure this out on, like, this little notepad, little notebook paper thing. And then I was like, no, let me put it on a big sheet. And then I was like, wait a minute, let me record it before I even figure it out. So now I'm recording before I even figure it out. Because I want to see if my hunch is correct. So, let's see. So the Catalan numbers, I gotta write down a few of them because I don't want to screw this up and, like, just write down what I think is the third one, but it might be like the fourth or the second one. So let me just write down, like, a few of them. But let's see. So Catalan numbers are 1. So I'm reading off my screen and I'm recording at the same time. So here we go. So they are 1, 1, 2, 5, 14, 42, 132, and I think we'll stop there. So I think so those would represent how many applications in a lambda calculus expression you would have. Sorry, that would be the input. So the index would be the number of applications, but the Catalan number would then be how many different ways you can arrange the applications. Now, if you have more abstractions, that means you have more possibilities for what the variables can be. So, for example, if you only have one abstraction, then all your variables, if they're de Bruijn indices, they're just 1. But if you have 2, then depending on how many variables you have that many permutations. So if you have 2 and then you have 2 variables, then you'd actually have 4 possibilities. So it depends how many variables you have, but how many variables you have depends on how many Catalan numbers you have. So if you multiply them together, or no, if you take the Catalan number, that's why it's its own function. If you take the Catalan number and you count how many, and then you take that and then you permute it based on, dude, let me think about this. So if you take, like, let's say you have 5 variables, right? So if you have 5 variables, kind of like X, Y, Z, let's say that's the first term, and another one that has B, so depending on how many you have, 5 would be the number of arrangements, not the number of variables. So 5 would be based on how many applications you have, but how many variables you have is different. Okay, so if I have, let's see, 1 application, 2, 3. So 3 applications gives me 4 variables. So the more applications, the more variables you have. And it might be like the number of applications minus 1 number of variables. So, but anyway, if you have like a context, if you have multiple contexts for those, then there's multiple. We'll just do it in de Bruijn indices because it's less confusing. So you could have, say you just have like 4 of them. We don't care about the ordering. You have, if you have one variable, then you just have one possibility. If you have 2 variables, then you have, you know, I think it's like 2 to the 4, right? Possibilities. So if you have 3 variables, you have 3 to the 4. So it's depending on how many you have. So number of variables to the power of, no, that's the exponent actually. Sorry, the number of possible, no, that is the number of, okay. The term variable is very bad for this. So the number of abstractions, okay, so the number of abstractions would be this number. And the number of variables would be this number. So it'd be the number of abstractions. I'll just write it shorthand. So number of abstractions to the power of the number of variables. And the number of abstractions equals the, that's going to be one of the major inputs. The number of variables is going to be 1 less, I think, or 1 more than the number of applications. So the number of applications plus 1. So there's 3 applications here. We have 4 variables. Okay. So, and then the number of applications also gives you the Catalan tree number. Now, I need to find out how this maps. Okay, so for C5, if you have 5 applications, I think you have 42. I think, based on what I see on the Wikipedia. So if you have, let's see here, they have for n equals 3, there are 5 characterizations. Okay, so here we go. So here's your number of applications, right? So we're going to define the function par. I'm just recording this in case it matches. If it doesn't, that's fine. I'm not offended. But if it does, this will be amazing, and I will not believe it. So, I mean, I will believe it, but it's just going to be like, I will have to be very astounded, but not like, I will have to accept the fact that this was not random, that, I'll explain later. But, so the number of variables equals the number of applications plus 1. So let's say the number of apps is A. The number of abstractions is I hate how they both start with A. We'll call it lambda. Okay. So the number of variables we'll just call it V. So V equals A plus 1, okay? And then lambda to the V is our number of, is going to be the par, I guess. So that means that lambda I lied. Hold on a second. So hold on a second. No, that's wrong. That's wrong. That's wrong. Lambda to the V is the number of possibilities for that Catalan number. Right? Right. So we want so we'll call that permutations. Okay, so the Catalan times permutations equals par, I think. Right? So then we need the Catalan number, which is, so the C is the Catalan function. So Catalan of A times the permutations, which is lambda to the V, equals par, I think. All right, so the Catalan number is going to give us how many grouping, or how many arrangements, and we multiply that by the number of variables. Although no, this is wrong because we have to subtract. This is actually wrong because there's so many different ways that you can put the variable in. So it's actually not the number of, so what I'm calculating here is not going to be the total number of expressions, lambda calculus expressions properly yet, because I'm not taking into account the fact that you can only count the permutations for that number. So this number would actually be higher. So, but let's just figure it out anyway, because if it's higher than 270, then that would be interesting. And plus, I might be able to just count it on my computer because I have an iterator function already programmed. And so I could count how many there are for that. So we had 5 par 3, so this would be 42. Or it would be 5. Okay, so if the A is 5 and the lambda is 3, we'd do that. If A is 3 and lambda is 5, we could do that. Lambda to the V, so this would be 3 to the power and 5 to the power of A plus 1, which would be 6, and here it'd be 4. So, and I'm assuming, based on how I would do it, actually I don't know if I would put the abstractions or the applications first. I think I've done both. But 42 times 3 to the 6. Okay, so that's 30,618. And then if we do it the other way around, that's 5 times 5 to the 4. so that's 3,125. All right. So neither of those are close to 270, but the 3,125 is a lot closer, and I wouldn't expect it to be more than like an order of magnitude, maybe. Because the Catalan numbers, you're going to have... Okay, well, let's think. Might have given me the easier one to deal with, because 42 trees is going to be annoying to draw. Not saying that I should be willing to do it, but if there's 3 applications, then there's 5 trees. I'm looking at the page right now. So I'm going to draw them what I see on the page. So I'm just gonna draw them. So we have, and I'm just gonna draw the roots. Or you know what? I'll draw the little leg things, but I'll just draw them as like legs. So the way this works is you have 4 variables, right? And then you have the rights and lefts, right? So you have all these different ones, but you can only put the abstractions. Oh, you know what though? That would make it a large number, because you'd actually have more. I have to account for the fact that there's more possibilities of where you can put the abstractions as well. So whatever 270 is, it's not the number of lambda calculus expressions anyway. But maybe that's okay, because maybe that's jumping too far too fast. So if you have an abstraction lowered down, man, these numbers are too big. Because 270, what would that be? Unless it's 270, unless 270 is the function that I'm missing. And 270 is actually the number of ways that you can permute the abstractions amongst the Catalan trees. How do we take that into account? Because if I can quantify this, that would actually be powerful, because you could number, without having to search through all the lambda calculus expressions, you could uniquely label every single one, and therefore you actually have a unique, basically almost like a constant time numbering system for every computation that exists. You could uniquely number, like put a serial number on every computation that exists, and know that all the serial numbers are ordered, and there's a 1-to-1 correspondence between possible computation expressions and the natural numbers. And that would be pretty cool, because then you could save them in databases or whatever. Like, you could do a lot of interesting stuff, use them as hashes. I don't know, like, you could do a lot of interesting stuff with that. But do we get the number 270 out of this at all? Or like, how does this, I want to see like how this works. So there's these 5 trees, right? And I want to get a different color so that it's easier to see. So the different ways you can order these, let's say for just one tree, right, is like you could have all three up here, or you could have, you know, one up here, one down here, or whatever. You could have them distributed however you want. But the higher they are, the more that these. So okay, so there's three. So out of this configuration, there is how many? Right? There's how many abstractions? If there's 5, then that means these 5 can appear anywhere in here. So there's 5 like factorial or something like that, because there's either put all 5 up here, or you could put 4 up here and then 1 here. It's like 5 choose 3 or something. I'm not too much of I'm not brushed up on my combinatorics, but it's something to do with combinatorics. But the problem is that you have to take into account that the higher up you are in the tree, the less children, or the more children you have that are affected. So up here it would affect all 4, but down here it would only affect 2. So, man, I wish I could record a moment of epiphany, but I feel like I have to now count, you know, what that is, like, or whatever. 5 choose 3 is only 10. So that means there's 10 possible ways that you can orient so there's 10 ways that you can orient these dots for each of these things, right? But there's also so if all 5 of them were up here, you would get the full 4 or 5 to the 4 power, which let's think about this. So 5 to the 4 power is 625. So 625 yeah. 5 to the 4 power is 625 ways that you can arrange all the variables if they're all up here. As soon as you start putting them down, you're reducing, you have to reduce them. And I don't know if there's a way to do that. I just thought of something. I should post this and then just say, I'm making a video where I'm tweaking out and I'm acting like I'm acting like a Terry Davis. That would be awesome. Be like me going all out Terry Davis style. Except that he didn't actually do this kind of thing per se, but the way he thought about things with the random number generator and all that stuff. It's like I'm acting Terry Davis-ish. Okay, so I'm gonna put this on pause, and I'm gonna remember to. I'm just gonna write down, like on the corner here, like 3 par 5. No, 5 par 3 equals 270. Because I still feel like there's something like. Is it like a multiplier? Like I could divide it by 270. I could take. What if it's this? And that's just a theory. But what if it's I take the number of total possibilities from each of these, right? So I take this number, right? Which is 5 to the 4, and then I multiply it by 10, and then when I like divide by like this like 270 or whatever by like the par, like that actually is like you divide it by 270, and then that divider, like that gives you then like the correct number of like it reduces it down the right amount for these numbers, that you get like the right amount, except that the problem is I would have no idea how to actually compute the 270 in the first place for like all the other numbers. I'd be like, I don't know the actual function for that, but it would be interesting if that's what it was. Like, it was like, wow, you divided by 270, and wow, this actually works. Like, it'd be interesting. So, see you guys later.